Very few, I mean, less than 20 or 30 students got it correct. But we also cross-verified. I think the answer is correct only. Uh, Maybe this is not a good time to do it. Maybe one of our TS sessions we will try to solve it in front of you. Okay, since this is very short session, if I sit and solve, I think more than 15 or 20 minutes will take, uh, and we'll get less time to go through week 7. We have noted, we will note this down. Okay, so I will note this down. In the coming Tuesday TS session, we will try to solve it. Okay. Is that okay for you all?
Yes, sir. Okay.
Okay. Yeah. All right. So we'll begin. And today is the deadline for week 6. Okay. So submit your week 6 graded assignment solutions. And you should start watching week 7, which is very, very lengthy. Right. It has some 10 lectures to go through. But the contents are reasonably okay. Okay. So even though the lecture count is very high, the contents that we discussed were very well known to you guys. Okay, so in week 7, the concepts in week 7 that you have to focus on are you should really understand what series is. Okay, and in that series, after you observe the series, you should be able to classify them as convergent or divergent. Okay, and there are different tests that we are going to study. So to conclude this convergence and divergence, there are 3 different tests. First one we are going to study is comparison test and ratio test and root test. Okay, so these 3 different tests will tell us whether a series is convergent or divergent. And again, series and power series. We have to see power series. Both. And then the next important concept. This is really important for your exam point of view, which is radius of convergence of a power series. And strong note that the radius of convergence, you should only talk on a power series, not on a series. Okay, so this ROC will exist only for power series. Okay, so do not get confused, and we will see all these things in detail. Okay, so before I begin, just to understand the crowd, how many of you have already started watching week 7? Can you just raise your hands? Okay, one. Anybody else? So the question is, how many of you have already started watching week 7 contents? At least the week 1 lecture 7.1, week 7, 7.1, 7.2. Nobody. Okay, only one. All right. Then I will try to give you a short summary, and we will mostly try to cover this part. Okay, so series and power series. What are series and what are power series? And we will see few examples which are very well known examples for us again. And we will end today's lecture. And on Sunday, we will solve problems along with discussion on this radius of convergence. And also there is a different class of functions which we are going to introduce, which are called exponential functions. This is also really important. And yeah, so these are the main concepts that are there in week 7. Okay. So let's begin with series. Now I will walk you through week 3 now. So in week 3, we have talked about sequence of a real numbers. So bring all your knowledge that you have gained in week 7, week 3, which is sequence of real numbers. So what is sequence of a real numbers? How does it look? It is denoted like this, an, right, within the third brackets. And what is this mainly? This is a sequence of real numbers. That means it will have a first term, a0, a1, a2, a3, like this. It's a sequence of real numbers. It won't end. So there is no ending point. So there will be infinitely number of real numbers which are arranged in a sequence. So this is a sequence. Now with this sequence, we are going to generate a new sequence. Generate means we are going to construct a new sequence which is like this. So the first term of this new sequence will just be the first term of your original sequence, earlier sequence. So let's call this old sequence, and this is the new sequence which we are going to generate from the old sequence. And the new sequence is generated using the old sequence terms. So the first term of the new sequence will be the first term of the old sequence. The second term will be the sum of the first two terms in your old sequence. And the next term in your new sequence will be the third term in your new sequence will be the first three terms sum. So a0 plus a1 plus a2. And the fourth term in your new sequence will be the sum of the first four terms in your old sequence, which will be a0 plus a1 plus a2 plus a3. And we can now start observing the pattern. So the next term will be a0 plus a1 plus a2 plus a3 plus a4. So the fifth term in your new sequence will be the sum of the first five terms in your old sequence. So like this, here the nth term will be an minus 1 because we started from a0. Okay. So nth term will be an minus 1. Here the nth term will be the sum of the first n terms in your old sequence, which is a0 plus a1 plus a2 plus and so on, an minus 1. So this whole sum will be your nth term, right? So there is a notation for this summation. Okay, instead of writing like this, we write the same thing like this. So we use this summation symbol, and there will be a variable which we label it as k. And for k, there will be a starting point and an ending point. So k starts from 0 to n minus 1, ak. So what does it mainly represent is, so you have to substitute k is equals to 0, and then from 0 to n minus 1 you have to substitute in place of k and add all of them. So what we will get is a0 plus a1 plus a2 plus and so on plus an minus 1. This is the nth term. And this is the shorthand notation for summation, summing of n terms. Okay. So now this new sequence, you can call it as Sn sequence, summation sequence. Okay. So Sn means this is S0, this is S1, this is S2. So like this will be Sn. Now, again, this also a sequence and it will not stop, right? It will go and so on and so forth. Now, what series is this? The last term of this new sequence that is formed. So the last term, I mean, the last term is like almost the last term is like you are adding up all the terms in this old sequence, right? And old sequence has infinitely many terms. So that means you are adding up infinitely many terms. That is what a series is. So this series is generated from the sequence, and that series is a naught plus a1 plus a2 plus, and sorry, s1 s1 plus s naught plus s1 plus s2 plus, and so on, plus sn plus, and so on, and so on, right? There is no stopping point. It will go till infinite. Okay, sorry, let me rephrase. So it will not be s summation. So this is the new sequence Sn, and the last term will be when n tends to infinite, right? So the last term of that sequence will be limit n tends to infinite Sn. And what is that basically? Sn is, Snth term is a naught to an minus 1. So as n tends to infinite, this will become a naught plus a1 plus a2 plus, and so on. It will not stop at an minus 1. It will go till infinite. So this is the series, and it is represented like this. N is equals to 0 to infinite an, or we already used n, so we will use k. So instead of stopping at n minus 1, we will go till infinite. This is what is called a series. And this series is generated from the sequence AK. Right? So every series has its older sequence, and from every sequence we can find a series. So series is basically summing up all the terms in your sequence, as simple as that. Okay. Now once we have a series, again the next question would be, when does this converge? And what do we mean by converge? Converge meaning, if you add up all the terms, is it going towards a unique real number, or is it going to infinite? So that is what this means. So converge, if it is convergent series, then our summation k is equals to 0 to infinite ak will be some L, where L is a real number. Okay. So even though you are adding infinitely many terms, the sum is actually converging to, or is going towards, a real number L. Such a sequences, such a series are called convergent series. Okay. So these, if this condition is satisfied, these series are called convergent series. Okay. So the very well-known convergent series that we know is this, you would have studied in your class 12, geometric series. How many of you have heard about this? Right, in your class 12, you would have studied geometric series. Right, how does it look? So one easy geometric series is 1 plus half plus 1 by 4 plus 1 by 8 plus 1 by 16 plus, and so on. Right? So this is a series. And if you, even though we are adding infinitely many terms, this summation will be equal to 2. Right? So this will go to a real number, and that is equals to 2. And in general, the geometric series is written like this. Right? So there will be a common ratio, which is R, right? And we are summing up. And this summation is equals to, what is it? Anybody? Come on, you would have studied this also. So 1 plus r square plus r cube and so on will be equals to 1 by 1 minus r. Yes, no?
Yes, sir.
Okay. So this is very easy, even though you forgot the formulas. You see, this is not the mathematical way, but you can use it. You treat this as s and you multiply r to s. Okay. What will you get if you multiply? R is multiplied to every term. So 1 times r will become r times r will become r square, r times r square will become r cube plus r power 4 plus r5 and so on. And if I subtract these two, on the left hand side I will have 1 minus r times s, and on the right hand side I will have all these terms will get cancelled out, right? The only thing that is left is this one. So on the left right hand side you will have 1. So from there you will get your s, which is the summation, is equals to 1 by 1 minus r. Okay, so something like this. And can I do this for every r, for any r?
No, sir. R
No,
should less than 1. Sorry, less than 1.
1, right? Because you see, when r greater than 1, you will see something like this. When r is 2, 1 plus 2 plus 2 square plus 2 cube plus 2 power 4 plus and so on. How does this sequence look? How does this series look? So 1 plus 2 plus 4. Every next term is bringing a very big number to add. So this will not go to a real number. This will go to infinite, right? But if you use the formula, what will you get? So 1 by 1 minus r. You're going to get 1 by 1 minus 2. R is 2. So you're going to get minus 1, which is absurd, right? So that is why you should be really careful when you handle infinity. Okay. So, or else you will end up getting some very strange answers if you directly use the formulas, which is trivially true. It is intuitively also trivially false, right? You are adding up positive numbers, and how can you get a negative number? So this is not correct. So geometric series will converge, and that will be equal to 1 by 1 minus r only if the geometric ratio is less than 1 and greater than minus 1. So the modulus absolute value of r should be less than 1. Okay. So finally, what we can say about geometric series is, so if you have a geometric series 1 plus r square and so on is convergent and is equal to 1 by 1 minus r if mod r is less than 1, and is divergent, and it will not be equal to any real number, is divergent if mod r is greater than or equals to 1. Okay. So that is about the geometric series. So even the geometric series is not convergent series always. So it depends on the common ratio r. Okay. So any doubt so far? So all
No, sir.
I talked about is the geometric series. Okay. So now Using this known geometric series, we can comment about convergence and divergence of some other series using the test called comparison test. So what we are going to do is we are going to compare the new series or the series which we have with the geometric series and conclude whether the new series that we have given is convergent or okay. So that is what comparison tests do. So for convergence, this is how we check. Okay, so you have a convergent sequence Cn, so convergent series. So let's say this series is convergent. Okay, and you have a new series, and each of the nth term. Okay, you have a new series an. Okay, again think like n is equals to 0 to infinite, and I'm not writing them, but it will always start from the first term to and it will go till the last term. So you have a new series an, and along with this, each of the term absolute values are lesser than or equals to this Cn. Okay, so the absolute values of this are lesser than or equals to each of the terms in this series, then an is then the series an is convergent. Okay, so what we said is you have a new series. Okay, if you if this condition is satisfied, all the terms, or maybe after a certain n value, if your terms are lesser than or equals to the terms which are already convergent. So even if this converges, any value lesser than that will also converge. So that is what we mean. For example, if you see something like this, so 1 by 2 into 3 plus 1 by 2 into 3 into 4 plus 1 by 2 into 3 into 4 into 5 and so on. This is definitely not geometric series. So if I have to conclude whether this series is convergent or not, I have to compare this with some geometric series which is convergent. Right? So I will construct, or I will see, I will compare this. This is an. N is equals to 0 to infinite. 0 to infinite. Now this Cn, I should have the terms that are greater than each of these terms. So if you see carefully, I'm going to take this particular series, right? If I take this series, if I take this series, now you can see that 2 times 3, which is 6, is greater than 2 times 2, which is 4. And both of them are in the denominator. So 1 by 6 will be lesser than 1 by 4. So our Cn is greater than, our C1 is greater than A1. Similarly, you see this term and this term. Compare these two terms. You will observe that this term is lesser than this term. Right? So there will be a lesser than. Similarly, if you see the third terms also, they will, this above term will be lesser than the below term. Like this, if you go forward also, all the terms in your first series will be lesser than all the terms in your next series. So this condition is satisfied right from the beginning. Okay. So what we can conclude is you see this Cn sequence. This is nothing but again a geometric sequence, geometric series. 1 by 4, 1 by 8, 1 by 16 plus and so on. Right. So this is a geometric series with common ratio 1 by 2. So if it is a common ratio 1 by 2, this will converge. So this converges. If this converges, then this will also converge. That's how you compare. So what we are going to do is we are going to compare our new sequence with a very well-known geometric series, new series with a very well-known geometric series, such that all your geometric series terms are greater than your new series terms. If it is happening, if you are able to come up with such a geometric sequence, geometric series, then your an, you can say that by comparison test, our series an will also converge. That's it. Okay, so this is about convergent. How do I prove, or how do I say the series is divergent? For divergence, the same thing, you have a new series with you. If it is other way around, if you have all your terms are greater than some dn, okay, so you have a new series an with you. Now you have to construct another geometric series which is divergent. We can also we can also construct a geometric series which is divergent, right? Your r must be greater than 1. That's it, greater than or equals to 1. So now what you have to do is you have to come up with a divergent geometric series such that all your terms in the series an should be greater than or equals to dn, right? Then an diverges if dn diverges. Okay, so all you have to do is you have to come up with dn series, this series which is divergent, and also all the terms of your divergent geometric series should be lesser than or equals to your new series here. Again, an easy example would be let's say you have mm, 1 plus 1.1, 1.11, 1.111, 0.1111 plus and so on. So let's say you have this. Okay. So what you have to come up with is, okay, just a second. Let's take a very simple one. Let's take this first. Okay, so this is our dn series, and we know this is divergent because our common ratio is greater than 1. Okay, and we will see some series. So 1.1. Okay, you can consider 1, 2, 3, 4 only. So can anybody give me any example for this? Okay, let me take Very easy one. Okay, let's take this only. 1.1, 1.11, 1.111, 1.41, and so on. So this is a series, and I can come up with a geometric series with common ratio 1. Right? So 1 plus 1 plus 1 plus and so on 1. So you can see that all your new series term, an series terms are greater than. So the first term is actually equals to, but the next terms are always greater than the dn series. And we know that dn diverges, hence an will also diverge. This is how we do the comparison and say that by comparison test, this 1, 1.1, 1.11, 1.111, this will diverge. Okay. Observe that this 1, 1.1, 1.11 is not a geometric series, but we were able to comment on the convergence of the series using the comparison test. And you should be very clear what kind of test you are using and how are you concluding whether it is convergent or divergent. Okay, so any doubts here?
No, sir.
All right. Okay. So for again, just quickly covering what we have done. So we have talked about series, and the series is generated from a sequence, right? Every sequence has its series, and every series is generated from a sequence. Okay, and there is a very good connection between the series convergence and the sequence convergence, its corresponding sequence convergence. Okay, so that we can see later also. Then we talked about geometric series, and we kind of talked about the first test which we are going to see in week 7, which is comparison test. So we use geometric series to compare and conclude convergence of new series which are not geometric. Okay, and there is another important series which we use the comparison test and conclude that series is also divergent, which is called the harmonic series. And trust me, harmonic series has failed many theorems. So every time we talk about some facts, we exclude this harmonic series. And you will see why.
Sir, is there only one way to check the series is divergent, like by through comparison only?
As of now, by comparison, but later we will see ratio test and root test. Even in that test, using those tests also, we can conclude it will whether the series is divergent or convergent.
Okay.
Okay.
So, okay.
Yeah. So there are different tests also to conclude the divergence of a series. Okay. So the harmonic series is this when an is 1 by n, which is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus. Just by looking at it, it might feel that every term that we are going to add is smaller value. So after certain terms, we will be adding 1 by 100, 1 by 101. And after many terms, we will just add this, right? So the usual feeling is after certain terms, it will just become 0. And this series should converge. That is what our intuition says, right? But the fact is, this series is divergent. And we are going to use the comparison test to conclude this series is going to be a divergent series. Okay. So let's do that. And the proof is really intriguing. So you just have to pay attention. And maybe after this proof, you will also get convinced that this particular series is a divergent series. And even the prof has explained it very nicely. But let me just show you guys. Okay. So since I said it is a divergent series, I have to come up with a series which those terms are lesser than these terms, and then that particular series which I'm going to come up with should be divergent. That's all I need. Then I can say by comparison test, this particular series will also diverge. So let's label this. Let's say this is the series n is equals to 1 to infinite. Okay. Now, see, we have 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus and so on. Now, what am I going to do is I'm going to group these terms together like this. I'm going to group 1 by 2 like this. But from then on, I'm going to group 1 by 3 plus 1 by 4 together. Then I'm going to group 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 together. Okay, so 4 terms together. Then next, I am going to combine 16 terms together. Sorry, 8 terms together, which is 1 by 9 to 1 by 16. Okay, so like this. And then the next thing will start from 1 by 17 and it will go to 1 by 32 plus and so on. So I'm just grouping them. Okay, so now I will be coming up with a new series which looks like this. Okay, so I'm going to take 1 half, and then instead of 1 by 3, I'm going to take 1 by 4 plus 1 by 4. Instead of 1 by 5, 1 by 6, 1 by 7, I'm going to take 1 by 8, 1 by 8, 1 by 8 plus 1 by 8 plus. Instead of 1 by 9, 1 by 10, 1 by 11, every term, instead of, there are 8 terms, right? All the terms I'm going to make 1 by 16. Okay.
So how are you writing like this?
That is what. So this requires some way. That is what I said. So it's like over years and years, they have come up with this proof. Initially, they were claiming that this is a convergent, but later many mathematicians sat together and finally they have derived or came up with this kind of proof which broke the real analysis. Okay, so this was not generated by me, not generated by any of the current mathematicians. It was already proven like this. So they have constructed this kind of, so it's a construction. Okay, so there is no mathematical model behind this or mathematical reasoning behind this. They have constructed this in this way and then just disproved that it is convergent. So why are we writing in this way? Because we need a series which is a divergent series where each of the terms should be lesser than your terms in your an. That is what we are going to do. So since I have 1 by 3 plus 1 by 4, if I take 1 by 4 plus 1 by 4, this is lesser than this 1 by 3 plus 1 by 4, right? Because 1 by 4 plus 1 by 4 is half. And 1 by 3 plus 1 by 4 is 7 by 12, which is greater than half. And even the same works here also. So 1 by 8, 1 by 8, 1 by 8, 1 by 8 will sum up to half. Whereas 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 is greater than half. Right? So all I am constructing is I am constructing a series which is divergent, and also each term in my constructed series should be less than my original series. So this is my original series that I have. AN. Okay. So again, I have 16 terms here. I will replace all the terms by 1 by 32 so that this term, this sum will be greater than this sum. Okay. So like this, I can proceed. And now what happens is you treat this as the first term, this as the first term in both the series. Then this as the second term, this as the second term in both the series. Then this sum as the third term, this sum as the third term in both the series. This will act like fourth terms. This is the fifth term. This is the sixth term. And so on. You'll get seventh term, seventh term. But the way in which we constructed, the seventh term of this series will be greater than the seventh term of this series. Because here in this seventh term, we will have the denominator, every denominator will be 1 by 64. And there will be 32 terms, which will sum up to half. Whereas here, it will have 1 by 33 plus 1 by 34 plus 1 by 35 plus and so on till 1 by 64, which is greater than half. So this combination, what will it give is, this sum will be greater than half, this sum will be greater than half, this sum will be greater than half. So I can always have some 2 and 2 power n terms clubbed together, and that sum will be greater than half. Okay. So that is how we constructed this. And we said, we see this, this dn will look like this now. 1 plus half plus half plus half plus half plus. And there will always be half adding to this particular series. And we know very well know that this will not converge. So if I add half, it will just move. If I add one more term, it will just move from there. So this will go to infinite. So this dn actually a divergent sequence, divergent series. And also the terms in this series are lesser than the terms in this series, the earlier series, which will eventually give us or tell us that this series AN is divergent. Okay, so the AN is 1 plus half plus 1 by 3 plus 1 by 4 and all. Okay, so all that what we did basically is we just grouped the terms together such that within the group, if you add up, if you sum up, you will get the value greater than half every time. Every group will be like that. So even this group will have, next group will also, if you just sum up, the summation will be greater than half. So like this, you will have always, even though you are adding very less terms, this will never converge. It will just slowly increase. If you see the stem plot of this series, so initially it will be 1, the first term. Then 1 plus half is 3 by 2. Then 1 plus half plus 1 by 3 is 11 by 6. So like this. So it will just, so the amount that it will increase is lesser, but it will always increase. Okay, so the shape will look like this. It will go till infinite. Okay, and this is the proof. And this is one way of proving it. And after this proof has come, there has come many different ways of proving this particular series is divergent. Okay. So that's about harmonic series, and harmonic series has different variations also. So this is just summation 1 by n, and there is another series which is 1 by n power q. So it's called series q harmonic series, or we'll just call it series. Okay. So it's like 1 by n power some q. Some q can be any real. It is no need to be an integer. It can be any real also. But what we say is, or what we can conclude is, when q is less than 1, okay, careful here. The sign will sometimes mislead us. The inequality sometimes mislead us. If q is less than or equals to 1, this summation series diverges. So diverges. Whereas when q is greater than 1, summation 1 by n power q will converge. So what does it mean is, when q greater than 1 is like, for example, q is 2. When q is 2, 1 by 1, summation 1 by n square, which is 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square, and so on. This series will converge. Okay. And when q less than 1 is like n power 0.9. So 1 plus 1 by 2 power 0.9 plus 1 by 2 power 3 power 0.9 plus 1 by 4 power 0.9 plus and so on. This actually diverges. Okay, so the proof goes in the same lines, just like how we proved harmonic series is divergent. Just in the same way, you can prove when q greater than 1 and when q less than 1, you can always find when q greater than 1, you can find a series which is convergent and all the terms in the series are greater than this a n terms, these terms. Therefore, by comparison test, you will claim that the series is convergent. Similarly, when q is less than 1, you will always find a series where each of the terms are lesser than your sequence term, series terms. Therefore, you will conclude that by comparison test, it is divergent. Okay, so these are three important series. First thing is geometric series, you should definitely know. Harmonic series, which is convergent series, you should know. And also this qth harmonic series, or summation 1 by n power q series, we call it as like that. So you should know when q less than or equals to 1, it is divergent. When q greater than 1, it is convergent. Now you can use all these three different series for comparison tests. Okay, so once you know these three series, whether it is convergent or divergent for different parameters that you have, you can use all three things to compare for new series, new kind of series. Okay, so we will use these three series for comparison tests, mainly these three. Okay, so finally, okay, before moving, is this okay? Right, so it will take some time to digest actually, but yeah, math will never go wrong. Okay, so the final thing in the last 4 minutes that we have, we will try to talk about the connection between the sequence an and the series an, series an. Okay, so this series is generated from this sequence, and what is the connection basically? So if your series is convergent, So if series is convergent, this will definitely imply that this sequence tends to 0. So that means this limit n tends to infinite, an should be 0. And that makes sense, right? So if you're adding infinite terms, after certain term, the amount that you add should be nullified or should be equals to 0. Right? That will only happen when your sequence terms become 0. So the value that you are going to add should be 0. So which implies, which is very trivial. So if series converges, then your limit n tends to infinite an, your sequence should go to 0. Okay. So that is one thing. And is this true? If your sequence limit is tending to 0, can I imply that series is convergent?
No, sir.
No, just now we saw, right? So our sequence 1 by n, if you take the limit, this will go to 0. Right? So this sequence, limit n tends to infinite 1 by n, we all know this will be 0. But summation 1 by n, the harmonic series, is not convergent. Okay, so this is no. So we can't say. Okay. But what we can say is if limit n tends to infinite an is not equals to 0. So if your sequence is not tending towards 0, which will imply that
Series
your
diverges.
series, yes, your series an diverges. So there is no need to use the comparison test or nothing of that sort. You just compute the limit of your sequence first. If it is not being equals to 0, then you can straight away say your series, the generated series from this sequence will diverge. Okay, so this is the connection between the sequence and the series. Okay, so on Sunday session, we will try to do or talk about the ratio test and the root test, which are the other two tests. And then we will talk about the radius of convergence. And we will also solve many problems in that particular session. So on Sunday. Okay. All right then. We'll meet on Sunday.
Sir, at the last line, why you wrote this that a n will not be equal to 0?
If so, it's like if that happens, like if
Oh,
your
okay, sir. But
sequence is not tending to 0, if it is going towards 1 or 2, if your limit of the sequence is going to not equals to 0 means any other number which is not 0. If it is happening, then your series is a divergent.
it means, sir, if an will be equal to 0, then it should be convergent.
No, that is what I told you. No? If it is that star thing, first star. If it is equals to 0, you cannot say series is convergent. You cannot say. Because we have the exception here. Just now we saw harmonic series. But what we can say is the opposite of it, like something like this. Equals to 0, we cannot conclude anything. Series may converge or diverge. But if your series limit is not equals to 0, I can definitely say that your series will diverge. So there is no series which can converge even though your sequence limit is non-zero. Okay, so there is no sequence like that, which implies that if your sequence limit is not 0, then definitely the series that is generated from that sequence will definitely diverge. There is no point of convergence at all. That is what this means. This doesn't imply this. So these two are different. This will not imply. Okay, so I hope most of you understand logic, right? So if P implies Q, Q implies P, negation P implies negation Q, negation Q implies negation P. Did you guys study about these things? Logic, math logic. Okay, not needed. But this is not same as this. That you have to understand. Okay, so if your limit is being equals to 0, then your series may converge or diverge. We cannot guarantee that your series will always converge. So there are series which can converge when the limit is 0. There are series which can diverge also, even though the limit of the sequence is 0. Okay, but in this case, your series will definitely diverge.
But sir, when an will be zero, which is a real number, then why it will not be converge always?
That is
How it
what,
will
no, we
diverge?
once you have an exception, then definitely you can't do, right? So this is the exception, the harmonic series example. So if you see 1 by n, this sequence limit is 0, right? This 1 by n here.
Yes, sir. The limit is
Yes,
0.
yes.
This is 0, but the series is not convergent, right? We have proved that also, no? Just now we proved. We have proved that summation 1 by n is a divergent series. It's not a convergent series. Okay, so one counter example is sufficient to disprove the statement. So the counter example is this. Okay, it is not always. So if you are claiming that this happens, it should work for every possible case. So there should not be any exceptions. But once you find an exception, then done, you are done. This statement is no longer valid. Okay.
Yes, sir. Okay, okay.
Okay. All right. Then yeah,
But
maybe.
sir, the thing is, if series converges implies sequence tend to 0. This is true fact, na?
This is true. So this is true. This is true, and this is true, and this is false. Okay. So there are three statements I have claimed here, but out of them, this is false. The other two are true.
Okay, sir. Okay, got it.
All right. Then we'll
Sir,
meet on. Yeah.
like just a question regarding assignment for week 6. There are only 9 questions in it, right? There is a typo in the question which talks about question number 10, but there are only 9 questions.
Oh, I think one of the question has some error, and we kind of removed it, I guess.
Okay.
Yes,
Okay.
yes.
Yeah.
Okay.
I think that would have happened.
Okay, sir. Okay. Thank you.
Yeah. All right then. We'll meet on Sunday. Thanks.
Thank you, sir.
Yeah. Thanks all for joining, and have a
Uh,
great day.
Thank you.
Shrikant sir,
Yes.
Thank you,
Yes.
sir.
hello.
Yeah. Yeah.
Yeah, I have query there. I have submitted week 5 assignment on the time before and written submission all that, but it's in the list showing null. I think.
I
So we don't
think